Okay, so let's continue our lecture. So previously I was talking about a special case that wave is incident normally, but in a general case, wave may not be incident normally. It may be incident at an angle, and that is the oblique incidence case. So let's look into the equations and the graphical representation of this case. So now we have a situation. So again, the coordinate system is drawn in the same manner. So this is z equal to 0, and this is the boundary. So this is medium 1, medium 2. So in a general manner, we will represent this medium by its properties. Let's say epsilon 1, mu1, mu2, and epsilon 2. So these are the characteristic properties of medium. So wave is now incident at an angle. Okay, so we can represent the direction of propagation of a vector. So this is incident wave. Okay, and you can clearly see that it is now incident at an angle. Okay, so for angle we will use this line as our reference. So this incident wave is making an angle equal to theta. So again, because there is a discontinuity at the boundary, so some part of the wave will be reflected. So this is going to be the reflected wave, and this reflected wave will make an angle of theta, and some part of the wave will be transmitted. So this is transmitted wave, this is reflected. This is making an angle of theta. So this oblique incidence case, we can divide this case into two parts. And it's important to understand the difference because we will end up with two equations. Okay. The first case, we call it parallel polarization. And second one is known as perpendicular polarization. So once you understand the difference, then it will be easier for you to write down the mathematical forms for these two cases. So what is the criteria to find out whether you are solving a parallel polarization case or perpendicular polarization case? So this is decided based on the direction of electric field. So in parallel polarization case, what we will consider that electric field E is parallel to the plane of incidence. Plane of I will explain what is plane of incidence. Okay. Let's define perpendicular polarization. So what is perpendicular polarization? In perpendicular polarization case, electric field E is perpendicular to the plane of incidence. Okay. Now with respect to this figure, respect to this figure, where is the plane of incidence? Okay, so plane of incidence is that plane which contains the direction of propagation and normal to the boundary. So I have already drawn this line. So this is telling you the direction of propagation. So this vector is lying in which plane? It is lying in the xz. And this is the perpendicular. So let me use a different color. This line, you can clearly see this line is perpendicular to this boundary. Okay, this is boundary and this is perpendicular. Okay, so this perpendicular and this line, they are both lying in which plane? They are lying in xz plane. Okay, so if I apply this definition to our case, plane of incidence in our case must be which plane? Xz plane. Okay. But you should need to understand this, that if someone if someone draws a figure and he change this and he represent this as xy, so then you will not say that plane of incidence is xz plane. Now the plane of incidence will be xy plane. Okay, so make sure that you understand the meaning of plane of incidence rather than trying to remember that why the plane of incidence is not always xz plane. It is xz plane because the figure that I have drawn, in that, with respect to that figure, the plane of incidence is xz plane. Okay? Because this vector and this normal, they make a plane, and this plane is xz plane. Okay. And now what will be the difference? In case of parallel polarization, we will assume that electric field vector, it is in this plane. So electric field has to be in the xz plane. And for perpendicular polarization, electric field will be drawn perpendicular to the xz plane. So of course, what is the perpendicular to the xz plane? It must be y-axis. So perpendicular polarization case, the electric field has to be in the y direction, or electric field will only have y component. But in case of parallel polarization case, because electric field is parallel to the xz plane, so if some vector is lying in xz plane, so of course it will have x component as well as z component. As an example, let me draw it over here so that you get the idea. This is xz plane. So if there is a vector, this is a vector. Okay, let me call it A. This vector is lying in the xz plane, so it's obvious that it will have z component and it will have x component. So in a similar manner, when you are solving problem of parallel polarization case, electric field will have two components, x component and z component. But when you are solving the case of perpendicular polarization, electric field will be perpendicular to the xz plane, and that is only possible if electric field is pointing in the y direction. So in parallel polarization case, electric field will have only one component, and that will be y component. Okay. So once you understand this difference, rest of the procedure is the same. Okay, so I will just go through it quickly by considering one case. So for parallel polarization case, okay, we will solve this case and then you will easily understand how to find the equations for perpendicular polarization. Okay. So electric field has to be in the xz plane. Okay. Now this is direction of propagation. The line that I have drawn, this line, this is telling you direction of propagation. Okay. So this is direction of propagation vector. Now where is electric field? Electric field has to be in the xz plane. Okay. And we also know from our previous discussion regarding TEM wave, and that was direction of propagation vector and electric field will always be perpendicular. If you remember, let me write it again. I mentioned this point in at the start of today's lecture, that K dot E is always equal to 0. K dot E is always equal to 0. So now this vector is actually K, the direction of propagation vector. So where will be electric field? Electric field must be perpendicular. Okay. So what is the possibility? Electric field can be pointing in the y direction, but I cannot take that case because I am solving the case of parallel polarization. For parallel polarization, electric field has to be in the xz plane. It has to be in the xz plane. So it means electric field must be in this direction. This is EI. Now you can see that this vector, this is electric field vector, and in which plane it is lying? It is lying in the xz plane. So that fulfill the requirement that electric field is parallel to the plane of incidence, which is xz. So electric field will be pointing in this direction, and where will be magnetic field? Now magnetic field is obvious. Magnetic field, electric field, and direction of propagation are always perpendicular. So electric field must be pointing out. Okay, so I can show this with this line, this rotation, that magnetic field will be pointing in the y direction. This is something which you know from your basic physics courses, that if something is pointing into the board or into the paper, so you represent it by cross. And if something is coming out of the board or out of the paper, then we show it like this. Okay, so this is into the page. Sorry, not into the page, out of the page. This is out of the page, and this is into the page. In this case, magnetic field is represented like this. So it means it is out of the page. And out of the page means this is x-axis, this is z-axis. So it means coming out must be the y-axis. Okay. So now I'm going to do the same thing. I'm going to write down the equations for incident wave. I'm going to write down the equations for reflected wave. And I'm going to write down the equations for transmitted wave. Same procedure. Once I am able to write down the equations for electric field, magnetic field associated with incident wave, reflected wave, and transmitted wave, I will apply boundary conditions. And those boundary conditions will help me to find out what is the relationship of these three waves. Okay. So electric field, EI, it is now a vector, and it will have two components. So it will have x component. So x component must be equal to E naught cos theta. Let me write these two equations, and then I will explain how you can write them. Okay, it's simple geometry, but I will explain how I am writing these equations. So these are the two components. Because electric field vector is lying in the xz plane, so as I explain it over here, that this vector will have x component and y component. So this is the x component and this is the y component. So what we are doing is we are assuming that this vector its magnitude is, let's say, E naught. So the magnitude of this vector is E naught, but it has two components. Okay, so what you need to do is you need to find out what are the two components. Okay, so there are two possibilities. You can resolve it like this. So let me draw it. You can assume that this vector will have this component and it will have this component. So this component which is pointing in this direction, it is the x component. So I can call it EIX, and this component, it must be pointing in the z direction, and because it is pointing in the negative z direction, so you can clearly see there is minus y. So this is z component minus y, it's minus because from our figure this is positive z axis and this vector is pointing in the z direction, so that is why we used. Okay. Now what is the direction of propagation? The direction of propagation vector is this one. Okay. Again, direction when wave is propagating, it is also having two components. Which are the two components? this component, and then this component. So as wave is propagating, it is covering a distance along z-axis as well as it is covering a distance along positive z-axis. So now what we will do, we will represent this thing by e power minus j, because it is a lossless medium, and you will end up with k1 is the propagation vector, and then because wave is propagating in the x direction, so x sine theta I plus z cos. Again, simple geometry. If this is the angle that it is making, so it means it will have two components. So with one component you will get cos theta I, and with other component you will get sine. Similarly, magnetic field magnitude, because magnetic field, as in case of this, magnetic field is pointing in y direction, so there is only y component, so I will say y component. How much is the magnitude? Magnitude must be equal to the magnitude of electric field, which is E naught, and I will divide it by the medium intrinsic impedance, and it is eta 1. And rest of the equation will remain the same. That is, propagation direction is same, e power jk1 x sine theta I plus z cos theta. Now I can do the same thing for reflected wave. Okay, so ER vector, the magnitude of the reflected field must be changed. So previous incident wave is E naught, so it must be equal to gamma E naught. And we are going to find out what is gamma. Okay, so the two components of electric field are, again, electric field is an x z plane, so it will have x component as well as z component. So you will have x gamma, and then cos theta plus z gamma E naught sine theta. In a similar manner, this is direction of reflected wave. Reflected wave is traveling in this direction. Now, where is the electric field associated with it? As we are solving the case of parallel polarization, so electric field associated with reflected wave must be in the xz plane, and because it has to be perpendicular as well, so we can consider that it is pointing in this direction. Let's say this is electric field, this is ER. So what will be the direction of magnetic field? Magnetic field will be now into the page. So I will represent it by cross notation. And now the equation will be with respect to this angle. Okay, theta. So you can see that in this equation I'm using theta. What will be the angle? So again, e power minus j k1. Why I'm using still k1? Because both reflected and incident wave are in medium 1. Okay, and this medium 1 is represented by this propagation constant k1. Okay. So what you will write down, this vector will become e power minus jk1, and you will have x sine theta minus z cos theta. Now, why we have plus over here and now we have minus over here? You don't need to remember this thing again. This figure is there. You can see that this is the wave, reflected wave is traveling like this. Reflected wave is traveling like this. So it is having x component. So it is, if I resolve this vector, it will have positive x component, and it will have a negative z component. This is positive z-axis, so this will have this component which is pointing in minus z direction. So that is why we have minus y. Now I can do the same thing for the magnetic field. As magnetic field is pointing in the negative y direction, so I will write down minus y, and the magnitude will be magnitude. This is the incident magnetic field. So incident magnetic field magnitude will be multiplied by gamma, and then we have e power minus jk1 x sine theta r minus z cos. And finally, for transmitted wave, we will have et. Now, the equations for transmitted wave can be easily extracted from the incident wave. Okay, all you need to do is, in place of theta I, you need to use theta t, because transmitted wave is now with respect to theta t. So this is one thing that you need to do. Another thing that you need to change is, in place of k1, you will have k2, because transmitted wave is now traveling in medium 2. And other thing is, incident wave magnitude is E naught, but transmitted wave magnitude will be incident wave multiplied with transmission coefficient. The rest of the equation will remain the same. So let me write it down, and then you can see what I'm doing. So ET will have X component. The magnitude will be T times E naught, and I will have cos theta T minus Z, and then T E naught sine theta T, and then e power minus j k2 and x sine theta t plus z cos theta. So now you can clearly see that how I have extracted the equation for ET from this. Similarly, H T, transmitted magnetic field, will be equal to Y, and it will be equal to T multiplied by E naught and divided by eta 2, because we are now in medium 2, and then e power minus j k2 x sine theta t plus z cos theta. So now we have complete equations. What we are going to do, we are going to do the same thing, and that is apply boundary conditions at z equal to 0. So the procedure is same, the procedure that we use for normal incidence case. So when you apply the first boundary condition, and what is the first boundary condition? That is, we need to apply the boundary condition on electric field. So N cross E2 must be equal to N cross E. And why we are using this condition? Because in the general boundary condition, this is 0. So that is why they are equal. So tangent component of electric field on both sides must be equal. On both sides must be equal. So this is our boundary, okay? This is the boundary at which I am applying the boundary condition. So where is the electric field? Electric field has two components. As you can clearly see, electric field has two components. Which are two components? It has X component as well as Z component. Reflected field has X component as Z component. Transmitted electric field has X component and Z component. This equation, this boundary condition is applicable N cross E2 means tangent component. So out of X and Z component, out of Z, there are two components. One is pointing in X direction, other is pointing in Z direction. So it's obvious that X component will be pointing in this direction. This is X component. So of course, X component is tangent to this boundary. This is our boundary, and EX will be pointing in this direction. So this is tangent, whereas Z component will be either pointing in this direction or in this direction. So it is normal to the boundary. So it means the boundary condition will be satisfied by the x component. Okay. So what we are going to do, we are only going to take the x component. We are only going to consider x component. Okay. Along with this, okay, and of course we will use this one, and because z is 0, so this factor will cancel out. This factor will cancel. So let me write it down, and then you can compare your answer as well. So from the first boundary condition, we will get cos theta e power minus jk1 x sin theta plus gamma cos theta e power minus jk1 x sin theta equal to t cos theta t e power minus jk2 x sin theta. So from where you will get this condition, let me write it down. What we have done is we have taken EIX plus ERX, and we have taken it to be equal to ETX at Z equal to 0. Okay. Similarly, what is the other boundary condition? That is N cross H2 must be equal to N cross H1, and the reason is JS is 0. So the tangent component of magnetic field will also be continuous. Now, magnetic field has only Y component. Magnetic field has only Y component. And from the figure, it's obvious that this is the boundary. So Y component means it will also be tangent to this boundary. So it means we can apply HIY plus HRY must be equal to HTY at Z. So if you use this condition, you will get 1 over eta 1 e power minus jk1 x sin theta I minus gamma divided by eta, not eta 2, it's eta 1 e power minus jk1 x sin theta r equal to t divided by eta 2 e power minus jk2 x sin theta t. This is equation. So by applying two boundary conditions, we end up with two equations. Now, these two equations can be further simplified by making use of another important result, and that is, if you look at these two equations, there is one thing that should not be there, and that is this factor. You can see this factor is there with every term. Now, what is the issue in this term? This term is telling us that this boundary condition, it depends on x. It depends on x. So it means it is telling us as if at every different point, this is x. Okay. So if I move along this direction, so it means x is changing. If x is changing, so it appears as if this boundary condition will change. But this should not happen, because whenever you say boundary, so it means every point is included in that definition. Okay, I don't want that at different points of the boundary I should have a different relationship. Just boundary conditions are applicable at all points of the boundary. So in order to make sure that this boundary condition remains same, what we want is that even if x changes, this term should remain constant. Okay, even if x changes, this term should not change. Okay, so it means if I change x over here, I want that k1 sine theta I, k1 sine theta r, and k2 sine theta t. They should always give me the same result. Okay, because when I change x, so I will change x over here, x over here, x over here. So what is the other factor that can change the result? If k1 sine theta I is different than k1 sine theta r, and it is different than k2 sine theta t, then this term can change. But if I put this condition that k1 sine theta I equal to k1 sine theta r equal to k2 sine theta t, then even if x changes, this factor will not change. Okay, this is another important condition that we need to use, and this is known as phase matching condition, because this factor is appearing in the phase part, so we call it phase matching condition. So in order to satisfy the boundary condition, this k1 sine theta I, k1 sine theta r, and k2 sine theta t must be equal. Okay, so if you use this condition now, so what you are going to do is use equation A, equation B, and let me call this equation C and equation C to find gamma and T. So what you will get? You will get the value of gamma and you will get the value of transmission coefficient. So you will get eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta. And this will be equal to 2 eta 2 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta. These are equations which are valid for parallel polarization case. Now, what is the important point that we can see is this oblique incidence case is a general case, and the previous case that we discussed was normal incidence case. Normal incidence case is a special case of oblique incidence case. If I want to find out what will be the result from this equation if wave, rather than being incident obliquely, so previously if a wave is like this, now if I change, so what I will do is so previously wave is like this, which was oblique incidence. If this case changes, so now rather than, so now if wave is incident like this, wave is incident like this. So this is normal incidence case. So this is theta I. So now what you will say, how much is theta I? Theta I is equal to 0. So reflected wave is like this. So theta R is also 0. And transmitted wave is like this. So theta T is equal to 0. So what will happen to this case? This theta T and this theta I will be 0. So cos of 0 is 1. So what you will get? You will get eta 2 minus eta 1, eta 2 plus, which is the same case that we derived independently for normal incidence case. Similarly, what is the transmission coefficient? It will be 2 eta 2, eta 2 plus eta 1. So you can see we can easily derive the normal incidence case from this general oblique incidence case. Okay. Now you can do the same thing and you can practice the second possible case, and that is perpendicular polarization. The procedure will remain the same, but equations will change because now electric field and magnetic field, their direction will change. As a result, the equations will change. Okay. electric field, magnetic field. So you need to make sure that you can draw the figure. So what are the important factors whenever you are solving such kind of a problem? The first thing is you must draw a figure. You must draw a figure. Okay. Without figure, if you write such equations, that is a clear indication that you have copied such equations from somewhere. Okay. Most of the students, they make this mistake that without showing any figure, they write these equations. So how can you write these equations if you haven't drawn a figure? Okay, so make sure that you draw a correct figure so that I can match your equations with that figure. Okay, if you have drawn a figure like this and then you have represented this as, let's say, y-axis and this as z-axis, and then you are writing these equations, so it means all of these are wrong. Okay, so make sure that whatever you do, there has to be some figure with for that, and then you need to make sure that your figure is properly annotated. Okay, if you sometimes just again, this is not related to this discussion, but sometimes in exam, if it is asked to draw a figure, so some students they draw a figure like this. Let's say, as an example, they draw a figure like this. So this is not complete information. Why it's not complete information? You haven't mentioned what is along x-axis, what is along y-axis. So without providing this information, how I will interpret your graph? Okay, so make sure that when, especially with respect to graph or visual information, whatever you are showing, it should be complete in all respect. Okay. Now moving on to the next topic. Okay, so this was all about chapter number 1 of our course. Okay, so I have completed chapter 1. I have gone through the main topics that you need to cover. But as I have mentioned in my start, that the course contents are the same as it was in the regular semester. So you should prepare for exam, keeping in mind that the course content is the same. Okay, so let's move on to the transmission line theory. Now, the idea behind transmission line theory is in your circuit theory, when you use circuit theory, what you assume is you assume that the circuit size or dimension is very small as compared to the operating wavelength. Operating. So your circuit theory is valid only because the circuit that you are using is size is very small as compared to the waveform. Okay. And the reason why it is because we have this simple relationship between velocity, wavelength, and frequency. So wavelength is equal to V by F. In circuit theory, because frequency is very small,